All right, ladies and gentlemen, I appreciate you finding your way to the Edmodo site and getting on for your notes that will be due in class for tomorrow, September the 5th. Again, I apologize for them being a little bit late. In the future, I will try to have them up at least a day in advance, hopefully 2 days in advance. So if you find yourself missing for athletics or co-curriculars or whatever, you can have the option of taking your notes ahead of time instead of falling behind. Today we are going to begin. Our first unit is a basic look into functions. This is not something new. We have talked about functions before, but as I said, it's kind of a beginning. We're going to get pretty deep into the topic of functions. We have to start somewhere. So let's begin. Remember, we're taking our Cornell notes, okay, Cornell format. The first thing you need on your Cornell format, if you remember, is an objective. Okay, and our objective today is the student will, or TSW. You can just put TSW. Master the concepts of domain and range and various aspects of functions. You'll also put the lesson date, which you can either put it today if you want to get in the habit of putting it the day where you're going to actually take the notes, or you can put it as tomorrow's date, the day we'll actually be working on this in class. Either way, I don't particularly care, as long as you get it done. Okay. The video is not going to spend a whole lot of time waiting for writing time. Okay, so if you feel the need and you need extra time, just press pause and then hit play again when you're ready to move on. Okay, we're going to start off with a couple of basic definitions. Okay, you already have these in your notes, but if you don't remember them perfectly, you might want to go ahead and write them down. Let's get that knowledge base back up to 100%. See if we can't get these memorized. The domain is the set of all the x values of a particular graph, and the range is the set of all y values of a particular graph. And if you remember in class, I gave you a little cornball way of trying to remember these. Look at the words domain and range. Domain starts with D, range starts with R. Which one comes first in the alphabet, D or R? Obviously D does. Then think about the axes involved. What are the two axes? X-axis, Y-axis. Which comes first alphabetically? The X does. Domain comes before range alphabetically. X comes before Y alphabetically. So the domain and the X belong together. The range and the Y belong together. So if you've had trouble keeping those separate in your mind, couldn't remember which one is which, maybe that'll help you keep it straight. All right. In a graph, okay, and this is where we get into some new stuff. In a graph, an open dot reflects that a point is not included as part of the graph. But if you see a closed dot in a graph, that indicates that the dot is included in the graph. Again, press pause if you need to. We're moving on. Okay, this is all supporting information. Okay, so that's going to be on the right side of your problem. You probably have domain in the left, range in the left, and definitions on the right, and then this supporting information about open dots and closed dots. In fact, you might want to put open dot and closed dot, those two terms, you might want to put them out in the left-hand side of your Cornell notes in case you have to scan for them later. You want to be able to find them easily. Okay. When we are answering questions that refer to domain and range, most of the time we are reflecting some sort of a span of values. It's not usually a single value or two single values. It's usually a collection of values. And so when we answer those, we are typically using some type of parenthetical notation. We use parentheses for things that are not included and brackets for things that are included. So something like an open dot in a graph would be a boundary, but it is a boundary that is not actually included as part of the graph. So when we're notating it, we would notate it with a little normal parenthesis. But something like a closed dot, it is also a boundary in a graph, but it's considered to be part of the graph. So when we notate that, we would use square brackets for a closed dot. I'll give you some examples here in a moment. Okay. So for example, if you were to come across this notation, okay, where you have parenthesis 1, comma, 2, bracket, we are basically looking at a situation here that it begins on the x-axis for a domain or on the y-axis for range, but the graph begins at 1. Okay, we come from negative infinity, and we do not run into anything to do with the graph until we get to 1, and then we continue on to 2, where the graph ceases to exist. It doesn't go any further than 2. Now the 1 has a parenthesis on it, meaning that 1 is a boundary to the graph, but with the parenthesis, it is not an included part of the graph. It is the boundary, but it's not part of the graph. 2, on the other hand, has the square bracket. That means it is the boundary as well, but it is included as part of the graph. Okay. If you ever have a graph that comes from infinity, from negative infinity, or continues on to positive infinity, okay, infinity is always considered to be an open location within an interval. Okay, and it's open basically because we cannot go to infinity on the number line and put our finger on it and say, there it is. It is an uncountable quantity. Okay, so infinity is always open. Anytime you notate infinity in an interval notation like these, you will notate it with parentheses, not brackets. Okay, now let's look at some basic examples here. Make sure we get the idea of how this interval notation works. Find the domain and the range of the graph below. You may want to jot these down and give it a try for future reference. Okay, so let's think about the domain. Domain is the collection of all possible x values. So basically, we are proceeding along the x-axis. And the question we are asking ourselves is, as we come from negative infinity on the x-axis, where do we run into the first x value for the graph? Okay, well, we can see that the first x value for the graph exists when x is at -3. Now, we're not talking about it actually being on the x-axis. It is simply saying, does it have x value there? And yes, there is an x coordinate that exists there. And that continues on until we get to basically the y-axis. After that, the graph fails to exist anywhere else with the x-axis. Okay, so what are we looking at? The graph begins at -3 and it ends at 0. Okay, x goes from -3 to 0, so those are our two values, -3, comma, 0. Now you need to think about the parentheses or brackets. The -3, should it receive a parenthesis, meaning it is not part of the graph, or should it receive a bracket, meaning it is part of the graph? It is a closed dot. What do closed dots mean? They mean they are included. So there'll be a bracket on -3. What about 0? Is 0 included as part of the graph or not? Open dot. Open dot means it is not included, so that part of the notation would get a parenthesis. So a representation of the domain would be bracket -3, comma, 0, parenthesis. Now, when it comes down to the range, we do the exact same procedure, only now we are looking at coming up the y-axis. So when we come up the y-axis from negative infinity, where do we first discover the existence of a y value? Right across there, the x-axis is the first time that this graph exists on the y-axis. Where does it continue? Okay, we have y values until ultimately we get up to y equals 4, and then the graph does not exist. So what should the notation look like? Closed on 0, so a bracket, and at 4 it should be open, so a parenthesis. So the range would be bracket 0, comma, 4, parentheses. Couple more. Let's think about the domain real quick. When you come from negative infinity, where's the first place it shows up on the x-axis? Once again, it shows up at -3. Will it be open or closed on -3? It'll be open. Open dot means that part of the graph is the boundary, but it's not included, so that'll be parentheses. Where will we finally run out of x values on this graph? Well, we won't. The little arrow on the end of the line means that the graph is going to continue on forever. So we will go all the way to infinity, and as we said, infinity is always open. So there's your domain. How about the range? Coming up the y-axis, where does it first show up at? Shows up at -1 this time. Where will the range eventually stop at? It will not. This line will continue to rise infinitely, so the range is going off to positive infinity as well. Another example, find the domain and range. Go ahead and push the pause button right now. Go ahead and take a shot at the domain and range, and after you do, press play again. Let's see if you get it. Okay, now on the domain, coming across the x-axis, the graph begins at -3 once again and continues all the way to 5. Closed on the -3, open on the 5. So the domain you came up with should look like that. Bracket, -3, comma 5, parenthesis. On the range, coming up the y-axis, the first time we see the graph is at 2, and it's closed at, I'm sorry, -2, and it's closed on -2, and then it continues on to +3, where it is open. So your range should have been bracket -2, comma 3, parenthesis. Okay, now another review definition. We had this the other day, but you may want to go ahead and jot it down again, especially if you don't have it perfect in your brain yet. Let's kick that knowledge base back up to 100%. A function is a graphable expression where each value of x has one and only one value for y. Okay. Now what this basically means is if you take any equation whatsoever, in this particular case we're looking at a linear equation. We know that it's going to graph a line because x and y are both in the first dimension. Okay, but in order to be a function, what this means is for any value of x that goes into this equation, there is no way that you can get more than one value for y back out of the equation. So for any value we can think of, and I just invented 3 and plugged them in there. You don't necessarily need to copy all this down, but you'll notice in each case I invented some positives and some negatives. You could pick decimals and fractions and all kinds of crazy stuff and plug them in there. For every instance where you invent a value for x and plug it in, do you ever get more than one value for y back out of the equation? No, one value goes in, one value comes out. This is a defining characteristic of what a function is. Okay, so any value you pick for x always will only produce one value for y if the equation represents a function. Okay, one last thing to look at is this idea is also often shown as what's called a mapping. Hopefully you've seen mappings before. Okay. What a mapping does is it's like a graphical representation that connects every value from the domain to its corresponding what's called image in the range. Okay, so you may want to write this down. Mapping is your definition or your term, and you have a definition. It connects every value from the domain to its corresponding image in the range. Okay, so let's show you what this means. Okay, the last function we just looked at, okay, that y equals whatever it was, 2x plus 1. On the 3 examples I picked, we plugged in a 1 for x, a 2 for x, and a -5 for x. Okay, those are x information. That is your independent variable. Remember, your x-axis is what we refer to as independent. The y-axis is referred to as dependent because the y value, the image, depends upon what the x value is going in. And in each of the cases, when x went into the function, a 3 was a result. When the 2 went into the function, 5 was the result. When -5 went in, -9 is a result. This is what a mapping looks like. It shows the two different sets, the independent variable x, the dependent variable y. The ovals are part of the mapping as well, and a mapping will draw lines from one set to the other to show how data connects from the function to the image. Okay, so each element in the domain should match up to only one element in the range. That is still part of the definition for a function. Each domain only gets one range. Okay. As a result, mappings make it very, very easy for us to determine if we have a function or not, especially if there's a bunch of points, a lot of plots. Okay. Here are a couple of other mappings. Okay, you don't necessarily have to write this down. Make sure you understand, though. The following are mapping examples of functions. You will notice that in the situation on the left, you have in the domain 2, 4, or 7. Does the 2 or the 4 or the 7 connect to more than one value for the range? In each of those cases, no. Each domain only gets one from the range. Over on the right side, we see a domain that has a 4 and a 2 in it, and they both happen to connect to the same value. Is this okay? Well, the definition for range says each domain can only get one range. Does it say domains have to have different ranges? No, it doesn't. Okay, so the domains can get the same range, but the same range can't get more than one, or I think I said that wrong. Let's look at the other side of this example before I confuse you. The following are not functions. Okay, here we have problems. Okay, like on the left-hand example, your domain is 3, 9, 2. The 9 and the 2 are okay because the 9 only gets one value in the range. The 2 only gets one value in the range. But look what the 3 did. The 3 tried to connect to 4 in the range and also 5 in the range. That is a big no-no when it comes to functions. The domain can't get greedy. It can't go get more than one. On the right-hand side, we've got major problems. We have one value in the domain, one x, that's trying to get 3 different y's. Okay, it's not allowed that. Each x can only have one y. Okay, last thing for us to talk about before we call it a day. Another way to check to see if you have a function is to see if the graph passes the vertical line test. I mentioned this the other day while we were going over our review stuff. So if you don't have it, here it is. New term, vertical line test. The vertical line test says that if no vertical line can intersect the graph in more than one place, then the graph is a function. And again, you don't necessarily need to copy all this down, but definitely ask yourself if you understand it. Okay, what we're saying here is there's 3 different situations. Looking at the positive slope line on the left, vertical line test would say, hey, if you took and drew an unlimited number of vertical lines through the graph, does any of the vertical lines ever intersect the graph more than once per vertical line? And you can very easily see, no, it does not. So is this graph a function? Yes, it is. It passes the vertical line test. The one in the center, okay, same thing. We're going to draw a whole bunch of vertical lines. But you don't even need a whole bunch, because if any line hits the graph more than once, that means we have one x value that has more than one y value, and that's a no-no. So the one in the middle, going to be not a function. How about the graph over on the right side of this page? Okay, vertical line test. You can draw as many vertical lines as you want. Does any one ever hit the graph more than once? No, they are all only making contact one time. So obviously the answers to these are the ones on the outsides are functions, the one in the center is not. Okay, here are 3 more, and again, you don't have to copy them down, but go ahead and hit the pause button on the video for a moment. Let's see if you can get the yeses and nos correct on whether these are functions. Okay, what'd you come up with on the one on the left? Is there any vertical line that will ever hit this parabola more than once? No. Okay, this one is a function because the vertical line test passes throughout. How about the one in the center? This one is not a function because, as you can see, there are vertical lines that make contact more than once, so that is not a function. How about the sideways parabola on the right side there? Is it a function? No. We're going to hit twice. That is not a function. So on this, you should have come up with a yes on the left and 2 no's on the remaining. Okay, I keep telling you one more thing, but this one is the last. Okay, one last thing. Once you go to all the trouble to determine if an equation or a graph or a mapping, whatever it is, once you determine it actually is a function, we put it into what is called functional notation. Okay. Now, functional notation is something that you've probably seen before. Okay, earlier we decided that y equals 2x plus 1 was a function because for any x we plugged in, we never got another y back. We could graph it, we could do the vertical line test, it passes everything we can do to it. It is a function. After you decide it is a function, there's a different notation that we could write it in, and typically that notation is f of x. Okay, y is simply replaced with f of x, and that is actually how you read it. If you're reading this equation aloud, you read it f of x equals 2x plus 1. What does it mean that we change the notation? It doesn't mean anything except that it has already been determined that this equation is in fact a function. That's all it does, and we'll talk more about what you can do with it and all that kind of stuff later on. But that's it. I appreciate you tuning in and taking your notes. Again, I apologize for this getting out to you a little bit later than usual. I will try to do better. You may have to give me until next week until I actually do better. I've got to get a little prep work done, get a little better prepared. But that's it. Bring your notes back to class with you tomorrow so you can get that easy first grade. Have a good night.